Mostly we will review what we did yesterday, because it was a bit faster yesterday and some of you could not catch up. So, today we want to to go a little bit slow, okay, and I will request him to show some more options that we are not using here, but you can use maybe later for some other cases. Okay. So, he will show here which one he is using, but he will explain some other options as well. Okay. So, these we will repeat yesterday's one, and also today we will apply another boundary condition like the oscillation flow. Okay. So, oscillation flow we can use couple of ways. One way is to write a user defined function that normally we use, but today he will show you how to apply some Excel file or some data, discrete data into the inlet. So, he will explain it. So, and also because we need to assess you, you will get certificate. Okay. And I think this course will be recognized many of your institute. So, you have to give us all the assignments we are giving to you, you need to finish it and then just send to us. So, our tutor will give you some link where you need to upload. So, he will tell you in details. And also when you produce some data, for example, day before yesterday you did some MATLAB coding and you got some results and you showed me in your computer screen. Just take in a Word file and explain a little bit the results you got, okay, from your own word, what do you understand from there. And also yesterday you got some results, you need to have some explanation, the stream function and some other pressure and some wall shear stress, you got the results. You just a little bit explain why it is happening and why it is happening, just write it what you like. Okay. So, this way make a report like that and then just submit maybe on Saturday when we finish the final submission, and then we will mark you. Okay. So, now I am giving to the tutor, he will explain.
So, regarding the assignments and for that submission, I will share with you a different mail ID and you will have to submit that assignment in that mail ID. So, please submit it. So, combine all the assignments together in a single Word or PDF file and submit. Only one file you will have to submit, combining all this together. And for the Ansys simulations, you do not have to upload this Ansys file, just like snip the results in the Word or PDF. So, yesterday I shared with you two txt files, one is for I think velocity and another one is for flow rate. So, you can download those two, and for today I will be recapitulating yesterday's simulation, and today's main focus is pulsatile flow simulation. So, yesterday we took flow rate to be 0.12 meter per second, but today we will be doing pulsatile flow, that is the velocity is periodic in nature and it will vary with respect to time. So, this is the pulsatile velocity waveform. So, the waveform, if you plot that in Excel, you will get similar graph. So, this is periodic in nature, where the time period is 1 second. So, we have actually normalized the time period. So, generally it is around 0.8 to 0.9 second, but that we have normalized that and taken the time period to be 1 second. So, this is the pulsatile flow waveform. So, today we will again start from the geometry meshing, because yesterday I was too fast. So, I will be recapitulating those and I will show you how to give pulsatile flow. So, we will be not writing the UDFs like the user defined functions. We will, without writing UDF, I will show you how to give pulsatile flow as an input. So, first select this fluid flow fluent from this analysis systems list, just drag and drop. So as I am doing, you also do in your own laptops. So today I will go slow by slow. So now I will be doing it for the straight channel, and I have already shared the bifurcating channel geometry with you. So for practice you can do it with bifurcating channel geometry. So this pulsatile flow simulation, it is not possible to complete within this 2 hours time period. So you can do it at home. So it will take overnight to run the simulation. So if possible you can do, or you may not do. So depending upon the configuration of your laptop. So right click on this geometry and then select new design modeler geometry. So just tell me once it is done, so that I can proceed. So select any one of the planes after that. So I have chosen the xy plane, you can choose any of the planes, z, x, y, z. Then go to sketch, sketching option, and select the circle. So for drawing a straight channel, first we will have to draw a circle and then we will have to extrude in order to get a cylinder. So then click on circle and bring the cursor to the origin and draw a circle.
You can see a P. Okay, P means it is on the center. You can see P. Just go there. Yes, a P. P means it is on the center. Otherwise, it will move.
So then click on dimensions. So here we will be giving the diameter, prescribing the diameter of this circle. So you can see D1 over here. So and in this list you can see the D1 value. So you can change it to 3.4 millimeter. So yesterday we took 3.4 millimeter. So now I am taking that same value. So from here you can see that in my Ansys it is by default it is showing meter. So I will have to convert that into 10 to the power minus 3 to give it in millimeter. So just check whether yours it is in by default it is meter or something else. If it is in millimeter, then you will have to give only 3.4.
Or you can change it in the workbench.
Yes.
In the workbench there is a unit, so you can change it. It's better because here is in the meter. When it 0.0034, it will be tiny, very small. It's better to change the dimension.
So this is the circle, this blue, light blue colored one. Then go to extrude. In the top right, in the top left, you can see extrude. So click on extrude, and you will see that the blue colored circle turned to yellow. That means it has already been selected. So just click on apply over here. in the bottom left. Did you click extrude? So you just see that whether your circle is in yellow. So just click on apply. Here after geometry there is apply and cancel in the bottom left. So did you find it? Can I proceed? Yes. So click on apply over here. So once you click on apply, you can see this depth, FD1 depth greater than 0. So from here you will have to choose the length of the cylinder. So the length will be 10 times the diameter for this simulation. So it is 34 millimeter. So I am converting it into meter. And then click enter. So now you can't see the cylinder. So for visualizing the cylinder, click on generate. In the top you can find this generate option. So yes, so our channel has been created. For zooming in and zooming out, you can use the mouse zoom, the scroll in the mouse. So after creating the geometry, just close this. And in between, please save the Ansys files, because if it hangs, then everything will go.
Okay, just one thing I want to show you here. Can you take from the bottom the mesh individual component? What is the mesh? They should have, take this one. So I always follow this strategy, because when you want to do some mesh dependent test, I think it's a better option. You have a couple of meshes. Okay. If you only use only one, then if you change anywhere, everything will be changed. You cannot have different results. So it's better like a mesh 1, mesh 2, mesh 3. And then you can solve 3, and then 3 different kind of results you can get. Okay, now he already has the geometry in there. Now connect the geometry with the mesh. Yeah. Connect the geometry with the mesh.
For connecting the geometry, just click on the geometry and drag it to that geometry.
So
just click and drag.
Now this geometry connected to this one. So now if you can make the mesh, this mesh will be different than the mesh there on the bottom, if you make different meshes. So it is very, very good way to organize those things in one screen.
So we can have the parametric just for the...
Yes, that's true. You can also do the parametric study. Yeah.
So for grid independence test, you can use like this. So since now we will not be doing that, when going to this mesh. You know, you already like then zoom out. Zoom in.
Take this one to take it down. The other one, Prof.
Has anybody not completed up till this geometry creation? So can I proceed towards mesh? So just double click on this mesh. So after opening the mesh, just click on mesh and then click on generate at the top. So you can see the meshing, but it's very coarse mesh. We need to reduce the mesh size. So for that we will be doing body sizing. So just click on right click on mesh and then click on insert and then select sizing. So here you can see, can you see these green colored boxes? So this is for the point selection, for vertex selection. This box is for edge selection. This is for face selection and this is for body selection. So I am going to select the entire body. So I will click on this and then click on this in order to select the whole body. Then go to geometry and click on apply. And you will have to change this element size. So I am changing it to 2 into 10 to the power minus 4 meter, the element size.
Yeah, it's a bit tricky, so you have to like play with it. Okay.
Yes, you will have to play with it, but since I have done the simulation before, I can guarantee that this is the mesh size. Then again click on mesh and click on generate. So you can see relatively uniform meshing, like towards the wall also the mesh size is same as that of the center, but towards the wall we need more finer mesh. So we will be adding inflation layers because the main parameter of importance is the wall shear stress. So we need to have mesh at the wall very finer than that of the other regions.
So you know the reason why we need the finer mesh near the wall, because all the gradient there, we need, if you want to capture that, we need a very fine mesh.
Anyone who has not yet completed up till this? So again right click on mesh and click insert, then go to inflation. Then again click on this entire body, like body select this geometry and click on apply in geometry. The next step is to select the boundary. So for the boundary selection we will have to select the walls, not the inlet and outlet faces, only the wall we will have to select. So just click on boundary and then click on the walls. And then click on apply. So, by default the number of inflation layer is set to 5, but I generally use 6 inflation layers and growth rate of 1.2, which means that the mesh just adjacent to the wall, the size of the mesh, as we move away from the wall, the mesh size will increase 1.2 times up till 6 layers. Then again click on mesh and then click on generate. So, you can count the number of inflation layers, like you can see clearly see that there are 6 layers created, 1.2 by default. You can also change that, like yes, depending upon you.
Very interesting. Did you observe that the surface mesh, it was like a rectangular mesh before, I mean hexa mesh. Now it changed it. Just see the surface. Is it the outline? Yes, surface mesh already changed. So that is the problem here. It is very hard to control which mesh you want. Okay, so that's why now you see the Ansys discovery. It's a very nice one. You can use that mesh if you really want to make it hexa mesh. Otherwise, it's very hard to control. Okay, so that's, you see, the automatically change it. When we apply the inflation, the hexa mesh changed to some, I think, the hybrid, some triangular mesh or tetrahedral mesh or some hexa mesh. So yeah, if you really want to do that, or ICEM, use that one.
So, the next step is to name the inlet and the outlets. So, for that we will have to select the face over here. So, this naming is important because in the future we will have to add the boundary conditions. So, for that the naming is important.
Yeah, if you don't give the name, not a problem, it will work. But when you go to fluent and give an inlet condition, you can't get the inlet. It will be like one body, on surface. So that's why it's better to like give the name.
So, just click on right click on this face and then select create named selection. Similarly, other face you can name it as outlet. Right click, then click on create named selection. So, wall you may or may not name, but I normally prefer to name the wall as well.
That's good idea.
So, again click on this circular face and then right click, create named selection, name it as wall. So, just click on this name selection and this plus sign in the left. So, you can see the 3 names, like the inlet, it will get highlighted in red color, inlet, outlet and walls. Anyone left? So, just close this machine.
Yeah,
So-
yeah, I don't know, is it a bug or not, I don't know, but every time if you do the meshing, it is not automatically ticked. You have to like update here.
Yes, like geometry, you can see a green tick,
You saw the tick.
but for meshing, the green tick has not yet come. So
Yes, so
just
you have
right click on mesh and then click on update. So for example, you need different mesh sizes to.
That is for example.
Yes, that is for example. So now we will go towards the setup. So just double click on this setup. Select double precision, but if your system is having less RAM or is of i3 processor, then do not select double precision.
And as I told you yesterday in my lecture that the dimension, you see automatically the 3D is ticked because it's actually understand that it's a 3D geometry. So automatically tick, you don't need to do it. And double precision, yeah, it is your choice. And can you just do
Yes.
the parallel?
You can see the number of processors, like the number of cores in your system. So normally the laptop contains 4 cores. So you can parallelize the Ansys code. So, but don't put. I think it is better to put less than 4 because it will take the entire space. So just you will put 1 less than the maximum limit. So for now, since we will be okay, we can do. For now, for my case, I am taking is 2. So for the workstations, like for in your institution, you may be having the workstation. So there you can take it up to n number of times, like 20, 30, even 50, 80.
If it is needed.
If it is needed, yes.
Can you show the console? Go it up while the mesh is given. Yeah.
Like mesh, we can just check over here. Just click on check. Or you can click on report quality. So here the quality of the, you can see the mesh quality. So as I said that in some version of Ansys, in the model by default it is given SST k omega. So you will have to change this to laminar because our Reynolds number is in the range of 600 to 1200. So for 0.12 meter per second it was in 600, but since today we will be giving pulsatile flow, so the Reynolds number will change from it will be less than to 1500. I don't know the exact value, but it will be less than 1500. So just double click on this and select laminar flow. And then click on OK. Then expand these materials you have a plus sign left in the left. Then expand this fluid. So by default air is selected in Ansys. So just double click on this air and rename it as you wish, and change the density and viscosity. So density, like yesterday, I am taking 1060 kg per meter cube, and viscosity to be 0.004 Pascal second. So change this to 1060. Like you can also do the power law or Carreau model, but since today our main focus is the pulsatile flow, I am just choosing the Newtonian one. But you can select, now also you can select the Carreau model and power law model, so for practice. Then click on change on create. So click on yes, like overwrite air, so we need to overwrite, and then click on close. So the next step is prescribing the boundary condition. So for this particular problem, at the outlet we will be using 0 gauge pressure boundary condition only, but in reality we have pulsatile pressure at the outlet. But I will be demonstrating only, I will be giving only pulsatile velocity at the inlet. In similar way you can prescribe pulsatile pressure at the outlet in a similar manner. So please download that velocity.txt file which I shared with you. Now we will be requiring that. Like this is the file which I have shared with you. So you can see that the maximum flow rate I think goes up to 0.19, 0.2 meter per second, and the minimum is around 0.05, something like that. So 1.12 which we took yesterday is the mean value, like the time averaged value. So please open this text file. Now we will have to edit this text file. So did everyone open? So in the top row you just press an enter, and in the top row you type two names, like what the first column and the second column is representing. So the first column represents time, and do not use space key, use the tab key and then enter the names. Like do not use space, use the tab key. Done. So again press on enter, and in the top first I am writing the things by using the tab key, then I will explain each and everything. Yes. So first I have written velocity, so this you can write any name, but it is advised don't use space, just do not use space because Ansys may not recognize space. So any name, but it should be a continuous name, any name you can give. So after putting tab I have written 2. 2 means how many parameters are there. So for our file we have only 2 parameters, time and velocity. So I have written 2. So this is the standard format. In this format only we will have to write the .txt file. Then again press tab and there I have written 101. So, how many data points we are having? We have total 101 data points starting from 0 to 1, starting from 0 to 1 at an interval of 0.01. So, we have total 101 data points. So, the first column, the first velocity represents the name, the 2 represents the number of parameters, 101 represents the number of data points, and the last one represents periodic or non-periodic. So, since this is a periodic flow, so we have prescribed 1. For non-periodic flow, you prescribe 0 over there. So, this is the format in which your .txt file should be, otherwise Ansys will not recognize it, you will have to write UDFs. So, save this after that. And also save your Ansys file, there is a reason why I am saying this. Has anyone not completed up to this step? So, just copy this velocity file. So, you will have to paste this in a particular location. So, I will just show you where you will have to paste, copy this velocity file. Yes, so when you save Ansys file, you will see this workbench file, like I saved it in the name straight channel pulsatile, and also you will see this folder is created, straight channel pulsatile files. Like in whichever name you will you save, you will see underscore files name coming. Did everyone find this? So, just click on this, then select DPO. Then select FFF and then open Fluent. So, paste your .txt file, the edited .txt file in this location.
So, this is the place where your Fluent file will be saved. If you save sequential file, it will be saved here in this directory.
Yes.
Triple S.
Just tell me once it is done. Yes, it is for patient specific simulations you will need to give pulsatile pressure at the outlet, but here just for demonstration I am giving 0 pressure at the outlet. Particularly for the FSI simulation, the pressure value is very important. So, this is rigid wall simulation. Today I think Suman sir has talked about FSI simulation, FSI fluid structure interaction. So, for fluid structure interaction we need to give the exact pressure values, otherwise the deformation will be not correct. So, generally like the minimum pressure is 80 millimeter Hg and the maximum is 120 millimeter Hg for a normal human being, but it can vary. Yes. So for converting that to Pascal, right, 133.2 I think you need to multiply it with. So maybe tomorrow I will be showing the FSI simulation. So in that FSI simulation also we will be using zero pressure only, but just for visualization we can do that, but for getting quantitatively accurate results we need to give pulsatile pressure at the outlet. So we need both pulsatile flow at the inlet and pulsatile pressure at the outlet. So has everybody completed up to this step? Yes. So in the now you will have to write some commands in the console. So place your cursor at the bottom and then type file. Type file. In the console type file and then press enter. Please check the spelling, because if you this is all standard syntax. So then type this command read hyphen transient hyphen table. So please check the spelling. Read transient table, in between there are hyphen. Then press enter. So here you will have to write the file name .txt, in whichever file name you have saved your .txt file. So like you can see, I saved my file as velocity. So I will write velocity.txt over there. So .txt will have to write, means I do not know whether not writing .txt will work or not, I have not checked, but to be safe write .txt. And then click on enter. So it should read like this. So you have 101 data points, velocity, time, and like this. It should read like this, depending upon the name which you have given in that file. Has everybody completed up to this step? So the main part is done, like reading the pulsatile flow in Ansys is done. And another one thing I forgot to mention, since we are doing a transient simulation, select transient over here in Ansys. So by default it is steady, so just click on transient. So now double click on this inlet. Now we will be prescribing this inlet boundary condition. So if you like, we have velocity magnitude, and if you click on the drop down, you can select, you will have to select velocity, means depending upon the name, this name will change depending on in which name you gave in your .txt file. So select this one. Then click on apply and then close. So double click on outlet and check whether it is 0 gauge pressure. So by default it is 0 gauge pressure, no need to change anything. And wall, by default it is no slip boundary condition is prescribed. But again I am saying that for patient specific simulation you will have to prescribe pulsatile pressure at the outlet. In the similar way you can also upload the pressure .txt file and then select the pulsatile pressure from there. So now in the methods, like similar to yesterday's simulation, select simple and keep the default settings like second order upwind for momentum and first order implicit for the transient simulation. So keep the default settings. Just choose the scheme to simple. If it is not by default, it is not simple. So you can choose actually any of the schemes, but since only simple algorithm is taught in the lecture classes, so it's better to use simple. So then click on this residual under monitors and leave it to be 10 to the power minus 3, because this is a pulsatile flow simulation. If you give 10 to the power minus 6, then it will take very long time. So leave it to 10 to the power minus 3 only. So then click on report plots. So as the simulation is progressing, we want to visualize how whether Ansys has really taken the same velocity which we have prescribed, means same velocity waveform which we have prescribed. So just double click on this report plots. So don't double click on the report plots, double click on this report definitions. Double click on this report definitions. Then click on new and surface report, then facet average. Facet average means cross sectionally averaged. So I am selecting the velocity from here, and I want to see, like we have prescribed the velocity at the inlet. So this is just to confirm whether Ansys has really taken that velocity which we have prescribed. So click on this inlet option only and then enter. Okay, okay. Is there anything below new surface in your screen? There is an apply option, right?
Into console. Otherwise,
Yes, yes, print to console. And no, yes, that is no, no need to print to console. You can see it in this, like now you are. We don't need to print to console. Like here you are seeing the geometry in similar way you can see, but where is the apply option?
Enter it and see. I think already applied.
Yes, so it has already been applied. Yes. So everything is now set up. Now we will initialize the solution, but do not start the calculation because I will show you another one step. So just do the initialization. You can do hybrid initialization. You can initialize the solution. Do not start the calculation. Then double click on auto save every time steps. So for this particular simulation, we will be taking the time step size to be 10 to the power minus 3 seconds. So I need to save every suppose 100 time steps. So depending upon the space of the system which you are using, you can prescribe. So I want to save every 100 time steps, like in between if the simulation stops, then you can start the simulation from the middle. Otherwise your whole data will be lost if you do not do this step. So since my time step size will be 10 to the power minus 3 seconds, that means for one cardiac cycle I will have 10, I will save 10 data at 10 intervals. Then click on OK. So I am just saving it before starting the simulation.
So this one you have to be very careful when you choose this one, because once your simulation is done, if you need some intermediate data, you have to run it again. So based on the profile, check which data you need for the explanation. Maybe the peak one, couple of peaks, couple of bottom, and then choose the time and just set up that time I need a data.
So it's actually better to save every time step, but since
every time step is so difficult because it's a
yes,
huge space.
Huge space, yes.
Yeah, you have to give a lot of space, and also your simulation will be very slow down because it will save and take some time. Yeah. So just do some calculation before you do that. Just see the what is your total time, and what is your time step size, and then you can calculate after how many time steps you want to save the data. Save more, not a problem. So help three ways. One way is if your simulation somehow stops somewhere, you can start from there. Okay. And another one is if you want to analyze some data in some specific time, because it's a transient case. So in a specific time, you can use the data in that time. And also if you want to make some animation, you can use the whole data set and you can do the animation. Yeah, there are 3 reasons.
So then click on run calculation, and here so we will have to first as I said, let me write the time step size. So it is better to take 10 to the normally standard research papers, it is reported that 10 to the power minus 4 second, but due to time constraint I am taking 10 to the power minus 3 second over here.
You also need to do a test.
Yes.
So like a well-dependent test, you have also need to do that
time step independence test.
Okay.
And I have observed that for the simulation to become steady, means not steady in terms like you will have a same velocity, like the pulsatile nature needs to repeat. So it is like quasi steady states. In order to achieve this quasi steady state, you will have to run it for 10 cardiac cycles. So if, yes, so if you run it for 1 cardiac cycle, you will not get the accurate value. So you will have to run it for 10 cardiac cycles and analyze the result of the 10th cardiac cycle. Only the 10th. The first 9 cardiac cycles you don't have to analyze.
Because there are some startup issue. You are starting
Yes.
from the beginning, from 0. So the next one is recovering. So recovering. At the 10th one, it almost the same.
So if we we will divide, so total 10 cardiac cycles means the simulation has to run for total 10 seconds. So I am choosing the time step size to be 0.001. So we will divide that 10 by 0.001. So it is coming 10,000. So now you can run, I think, up to 3 cardiac cycles. So you give 3000.
3001. Keep at the end 1. Then your last data will be saved.
Yes.
Is better.
You can do either. Like standard initialization, which what I know is that like for simulations you first prescribe an initial velocity, initial pressure. So you can check the initial values. If you select, like if I go to initialization and then click on standard initialization, so you can check what initial values they are taking. And hybrid initialization, honestly speaking, I do not know it. Ansys takes.
It all automatically they calculate.
They automatically calculate.
That's why it's hybrid.
Also, there is one complete from step. Do we have to specify whether it has to start from the inlet or not?
No, you don't have to
Yeah,
specifically.
you can also compute from inlet. That's also very good idea. You can also choose from there, compute from inlet. So that's another option. So then they will take the input condition from the z direction, z velocity. Do the initialization. Because the simulation is starting from inlet.
If we provide this type of profile, velocity profiles, whether they will take a constant velocity or that will be a parabolic type of profile?
So this profile is time dependent, means x axis we have time and y axis is velocity.
No, I am taking
So if we draw at a cross section velocity, so it will be parabolic. Yes, for this case. But so for example, when we will be doing simulation in bifurcating channel or channels having stenosis like like converging diverging channels, so in that cases flow separation can occur, so it will not be.
I am talking about the inlet.
Yes, it is parabolic.
It will be parabolic.
Yes.
No, we are not giving the parabolic. We are giving the average velocities every time.
Yes, but after simulation they by default take it to be.
It will be after a little
Yes,
distance
after
from
the developing.
But in the
region.
inlet, no, it is not parabolic. It is not parabolic because it is not possible to give parabolic. Parabola every time is very tough. So that's why he is averaging and putting there in every.
If they are taking something like a rectangular profile.
Yes, and they are
say
actually
a
averaging
constant profile at every point.
every point. So he is putting every point uniform velocity.
So normally we don't give parabolic profile. There is, I don't remember the name. Wormserly profile. So, normally it is advisable to give Wormserly profile because it is a pulsatile flow. For steady state simulation you can give parabolic, but yes.
Yeah, honestly it is very difficult. So if you really want to do that, you extend the domain.
Previous case I had done that. I have extended the profile.
Extend
Yes.
it, yeah,
And,
so that
even there
by this place we are going to fully develop flow. So you have to extend this.
But then the PW will depend on the time step also, because since it is pulsatile, so
Yeah.
let's say at one time the velocity was 5 meter per second.
Yeah.
So it will be a particular length which is the fully developed.
Yeah, that's why
At
you.
the time the velocity is 10 meter per second, so reach fully developed will be
Yeah, that's why you have to give in a safe position. So, but I don't think that there is some issue here because the pulsatile, there will be no like parabola because it's just making some chaos here already because they are putting pulsatile. It is not like uniform. They are putting.
No, but actually what's the condition in that way? Is it like a uniform flow is
They are giving actually uniform because from the heart when it's pumping, is everywhere the same velocity.
So it is not a
No, it is not a parabolic from the heart. It's just pumping with the same velocity. Make the maximum iteration
Yes.
200.
Yeah. So, here by default maximum iteration per time step means for every time step we will have to achieve converged solution. So, you just increase it to 200 or yes 200 because in 20 iteration it will not converge at least for the initial time steps, and for the later time steps it will converge easily, but for the initial time steps it will not converge for 20 iterations. So, then click on calculate.
When do we use this adaptive type of time advancement? Adaptive type of time.
For example, in situations where like you have some profile something like this, like the profile is initially this and later on steady. So, then you can use adaptive time, like here we do not actually require that fine time step, you can give a larger time step, but here we will require finer time step. So, like here you can see the velocity profile it will come. So, it is looking like a straight line because only 2 time steps have, oh no, okay. So, after every time step it will achieve a peak and then converge the residuals. So, it has already completed 8 time steps it has already completed.
So it is converging within 20 or 21 time scale, right?
Yes. So, it is better to prescribe that maximum iterations per time step to a higher value, even if it will not take less, then it will it's okay.
All of this.
Yes, it will not take all. But if you prescribe 10 to the power minus 6, then I think it will go up to at least up to 60 to 80. So, you can also try this for this bifurcating channel which I shared earlier. Tomorrow we will be doing FSI simulation, fluid structure interaction simulation for this particular case, then we will proceed to the patient specific case. Like I will share with you the patient specific geometry. Like here it is not possible to demonstrate how to create that patient specific geometry. So yes, I can share you some link where you can get an idea how to convert the CT or MRI image to the patient specific geometry. But here for this particular tutorial class I will share with you the geometry and then we will apply the conditions. So, I will in that simulation I will not perform the simulation because it is going to take a long time. So, I will be prescribing both inlet pulsatile velocity, pulsatile pressure and cardio model to get a feel that how will actual simulation will look.
Do you have the simulated results already?
So, I do not have the simulated results for this case because I only run it for one cardiac cycle maybe. So, I do not have the result for this case. So, after 1000 time steps is completed, you can stop the calculation, and then we will like I have chosen number of times like in the autosave I have chosen every 100 time steps to be autosaved. So, at least let it complete like 500 time steps, then I can go to the results and show you how to post process, means how to do the animation. So, many of you were asking about the slides. So, we will be sharing the slides. There are few typographical mistakes in the slides. So, we will check those and then we will share it with you. Transition. Actually, if we give steady at the fixed value, then Ansys will forcefully take that value down. But that is not the case. So if you apply partial pressure, we will also apply pressure. So like pressure, normally like pressure we get I will have to explain in detail. So maybe tomorrow in the tutorial because it's very long. Yes, like how we are getting the pressure waveform, how this velocity waveform. So tomorrow Suman sir will come in brief about this. So in the tutorial I will just how we will get this
So say we are not getting the function, this is like a user defined.
this is like user
But if you say validate with the patient maybe the difference in main data
so for the patient specific we will not get the other function. We will get the data I have shown or an example. So one thing you can directly use those data like the way which I have shown, or you can use MATLAB sort fitting. So you can get an equation of that, and then you can derive this.
but most of the papers we can use of they are very in terms of
Systolic pressure.
they are visiting
So I
those are like how to do
so PV like you can get if you know the PV value, you can directly apply the science. Or if you see the transition, then you will have to scale like you have the transitions, you have the diastolic pressure and the systolic pressure. Like normally when this pressure we get two values, one for the systolic, one higher value, one lower value. Depending on the higher and lower value, your pressure will change. Once it will scale up or scale down. So you can check the saved files in this DPO FFF fluent. So for my case, it has completed.
It is about 1700.
Yes, 1700 iterations, but only one data file is saved for the 100th time step. So at least let it save 200th one, then I can show you how to post process. One more time step it needs to save.
Why is the data saving?
So your data is saving in the same file where you have kept your .txt file, in the same folder where you have kept your .txt file.
Data is saved. You only get two. Your computer is faster. So your computer is faster. How many core you are using? 3.
So those who have already run it for like 500, where it is. So those who have completed, I said to run it for like 500 time steps. So you may be seeing like this, you can see up to 500. So you can check whether the files are saved or not. Those who have already completed for 500 time steps. So it is now around 1:30. So I am stopping the simulation, and with that one file only I am showing the post processing. So double click on this results. So just check this inlet, outlet and walls. Then click on this contour in the top. So we want to visualize, for example, the pressure only. So beside the locations, just click on the 3 dots and select, like press the control key and select all the inlet, outlet and walls, and then click on enter. So after that click on apply. So this is the pressure contour, like yes, this is the inlet and this is the outlet. So you can change the time step from here, like this. So you have this icon over at the top, this time symbol. So you can visualize the outcome at the saved time steps. So for me it's only one, so you can't visualize. And for animation, just beside that there is a symbol animation. Using this you can just run.
You have only one data.
I have only one data, so it will not.
Still you can do the one. Can you just click next to the string function? Left? Yeah. No,
This?
next one, yeah. Particle track, you can do that. Go there, the particle track. Yeah, this. No, not this one. Yeah, I could do one. Just fluid particle move.
Yes,
Some
you can
animation.
show.
I don't know how to do it here. It needs a file.
Yeah.
Can you just select the method not from a file? Just select. Is there any other option there? Yeah. No. Yeah. Oh no, not this option. Okay, leave it. Because that is not important.
So if you have suppose run the simulation for around at least for 3 cardiac cycles, then you can visualize for the last one. So can you visualize?
going beyond 3000.
So iteration 10,000, yeah, it will go beyond 10,000 iterations.
No, that is different.
That is different.
So you can start from there. I think they have one thing I need to make them clear. So one thing is from steady state, yesterday you did the steady state. For the steady state, what did you see? You see all the, like the continuity, the momentum, okay? All the residual was coming like this, right? And then after a certain time, when it reached to the residual value we choose like a 10 to the power minus 3, all this one, like all the equations come down to 10 to the power minus 3, then the solution stopped. Okay, that means the solution converges. And for unsteady case, we have actually two types of iteration. One called inner iteration and outer iteration. Okay, so it is different. That's why you see like it's like a pulsatile. Okay, you see in there. So this is steady state, and for transient case, what you see, you saw that you have like two things, delta t, the time step, and your like iteration, how many iteration per time step. Per time step, maximum number of iteration, you already have chosen 200, right? Maximum number of iteration per time step. And your solution is coming down from somewhere to your required residual 10 to the power minus 3, maybe within this value. If it is not within this value, that means your solution does not converge. But sometimes what happened is, within this 200 up here, when it is coming here and it is not coming down to 10 to the power minus 3, you are actually forcing it to converge. So sometimes they are actually confused. I think the solution is converge, but it is not converge. Okay? So you have to check that you see when the simulation starts, it starts with 200, 199, okay? It's coming down. So be careful, it is not up to 0. Okay? So mostly I saw this computer, it converging about 184 or 83, okay, going to the next time step. So that means the time step is called the outer iteration. So how many iteration we want? So how many time step we are solving? 3000. So that is the outer iteration, 3000. And each time step we have about like 20 or 25 iteration. So that is called inner iteration. So 2 iterations. So that's, you have to be very careful that sometimes it is coming here, is not coming down to here. So that should be the convergence line. It's coming here, but you told that the maximum iteration is 200, but it does not come here, then it's going back there and then coming here. It means it's not actually converged. So you have to check this one. Then you have to increase the maximum number of iteration. But there is another issue. Sometimes you cannot afford it. If every time step it takes 500 iteration, it takes long time to solve. So there are some issue. Okay, that time you have to do some debugging. Maybe your mesh issue, maybe your time step is very large. You have to make small the time steps, or your the relaxation factor you have to do. So a lot of things you have to think that time. So he is so lucky that his solution is like very nicely converging, but it is not always the case. Okay, and it is a very simple geometry, so it is easy. But when you are doing for complex geometry, it's sometimes difficult. Okay, and this number of iterations actually it's fluctuate. For his case, the profile he applied there, you see the velocity pulsatile somewhere is high. There is a very big peak. I think that time it will take more iteration. So, it is not like a fixed that it will converge within 20 or 25 iterations. So, it will fluctuate. So, it is always good. I generally, when I did my PhD, I use always 500. Okay, that is a safe zone, I just put it. So that my solution is converged. So if no 500, definitely some issues. So I had to look into it.